Yes, so these are the four types of polymers that we're going to cover today. They are addition polymers, in which for the most part, with polyurethanes being an intriguing exception, and I think it will make sense when we get there, but for the most part, not all of the atoms in the monomers make it into the final polymer product. And there's a very good reason why that's not true for polyurethanes. But in general, we have small byproduct molecules also being formed. Polyamides, as you'll already have guessed, are made of amide functional groups repeating. In that sense, there's some certain slight similarity to proteins, but only a very glancing similarity. To make an amide, we already know how to do that. We learned that in chapter 21. We learned that you can take an acid chloride and treat it with either a primary or a secondary amine. So I'm leaving these other two bonds to nitrogen unspecified, but we do need at least one NH bond for this to work. It won't work with a tertiary amine. And you will get an amide as a result, plus a molecule of HCl. I think you might also be able to do that by reacting an amine with a carboxylic acid, but you've really got to cook it. You got to practically pyrolyze it. It takes like hundreds of degrees. And then you would get also a molecule of water out of it, but certainly much faster and better with an acid chloride. So how are we going to get a polymer out of this? Well, we're going to play a little trick on this system. Instead of using an acid chloride and an amine, we'll use a diacid chloride and a diamine. And I just drew these as, representations here. The blocks A and B can be pretty much anything. But I think you see what's going to happen. Our acid chloride is going to find an amine to react, but there's another amine on the other side of the molecule, which will find another acid chloride to react with. But there's another acid chloride on the other side of that molecule, which finds an amine to react with, which is an amine on the other side of the molecule. On and on. You can see we're going to get a polymer this way. So just as an example, and again, I want to really focus on writing the structures of these polymers. But just as an example, I took this diacid chloride and this diamine, hexane diamine. And I should know what that diacid chloride is, but I don't. I'm sure you could look it up. There's a name for the, I'm sure there's a name for the benzene dioic acid, the paradioic acid. But in any case, this acid chloride will condense with an amino group, and then you'll have your 6 CH2s, and then your other amino group, which will condense with another acid chloride. And the name of the game with drawing these polymer structures is, well, we've already given the rule for that. You just need to make sure that all of the atoms that are in the repeating unit are represented within the parentheses exactly once, exactly once. That's what you want to aim for. Other than that, there's in general many correct ways to draw any of these polymer structures. I just did one over here because I was running out of room. But when we get to polyesters, I believe, I'll show you other correct ways of drawing these drawing a particular structure. But this is what we're trying to show here, right? The HCl molecules, of course, don't make it into the final product. They come off as byproducts, but the structure of the polymer, this is one correct way to draw it. You can think of it as on one side of your benzene ring, you have your acid chloride that forms an amide. Then you have your 6 CH2s and a nitrogen that forms another amide, and so attached to a carbonyl, but we have another carbonyl already over here. So as long as all of the atoms, and of course, as long as your structure is otherwise correct, but as long as all of the atoms in the final polymer structure in the repeating unit are represented within the parentheses, and don't forget the N, right? The N means it repeats an arbitrarily large number of times. But as long as that's the case, you're good to go. And like I said, we'll do at least one example in a moment where I'll show you multiple correct ways to draw any one of these structures. But that's how polyamides or nylons are made. And so uses of polyamides, well, synthetic fabrics, you knew that already. Kevlar, it turns out, is a nylon, a polyamide. So this, of course, is still available if anyone has questions, plus it's making it onto YouTube. Hi, YouTube. So yes, we'll include you in the screenshot, don't worry. But that will be available for your perusal later. Before we go on to polyesters, though, yes, very good. That was what I was going to give you by way, since I think we'll have the time here. That was what I was going to give you by way of a little practice problem session Why can I not find, oh, slideshow, let's see, from beginning. So just to review, and you'll get all 100 points for today just for attendance, but this is what I would like you to work on for a couple minutes. I won't let you sit there for too long, but what is the mechanism of this reaction? Always good to remind yourself of these. And as shown, assume slightly acidic conditions. I think that works out the best. And then see if you can draw the structure of the polymer that you get by reacting those two compounds. Okay, so like I said, I'm going to put this up on eCampus later. Actually, I have a few reef sets to put up. I'm a little bit behind on that sort of thing. Certainly, I'm hoping by the end of this weekend, certainly by the time you take the final exam, to get all that caught up. Good, so hopefully you came up with something a little bit like that for the mechanism. Let me just drag all these things out of the way. Of course, we protonate first using the conjugate acid of whatever our reacting partner is. Usually it's the solvent also. Then nucleophilic attack on the carbonyl carbon, so as to avoid getting O-. That would not make sense in acidic solution. At that point, we have a proton transfer. We only need one proton transfer because the leaving group is chloride. And of course, we're not going to protonate the chlorine. Chloride's a perfectly good leaving group. That's why acid chlorides are so reactive to nucleophilic addition and substitution. And then we simply pull off the proton using the benzylamine molecule, and we're done. So you've got the sediment of benzylamine. And again, the mechanism in forming the polymer is exactly the same. That very same type of thing will happen, just again and again and again. So over here, you see one of many, many correct ways to draw the structure of that polymer. There certainly are others, but it doesn't matter. I mean, as long as everything's connected correctly, of course, and the structure is always correct, but it doesn't matter the order that you show I didn't have to start with the benzene end. I could have started over here. And we'll do some examples of that in just a moment. But that will be, well, that will be up on eCampus probably today, provided I can log on. Anyone else having trouble with Howdy? Because I got I don't know, you guys might get these notifications too. I got the notification that I had to change my password, and I thought I had, and of course Bella Day is coming up. That was when she still had teeth. Oh, okay, that makes me feel a little better. Okay, it's not just me. Okay, so assuming I can get on to eCampus later, I also need to get on there if I have any hope of putting this video up on YouTube later on. I have to download the video and edit it first. But be that as it may, just a reminder, I am having office hours, but they'll be by Zoom using this same Zoom number. Canvas is also down. Great. So what about the grading I need to do today? Oh, brother. It always happens at the most perfect time. Same thing with OWL, of course, by the way. I remember one time we were having an exam the next day, and OWL went to, yes, I'm going to join in on that F. F for Howdy. Can you go back to the last slide really quick, please? Oh, you don't want to look at Bella? No, I'm just teasing you. Yes, I can go back to the last one. Let's see. But like I said, assuming I can get on, I can log on to Howdy, I'll get these up today. If not, then as soon as I possibly can. But I really was hoping to do a goodly chunk more grading today. Oh, it's actually not Bella Day the sequel. Well, crap. Let's just do Friday is Bella Day. We'll save it like that. That's one of the better pictures I've ever taken of her, and really shows you what her personality is like. I think that was probably around 2012, 2013, back when she had teeth. Which, by the way, if you're wondering about that, I had to have them all removed. The doctor said that they were all rotting away. She also said, which I didn't realize, apparently cats and dogs' teeth rot from the roots up rather than from the enamel down like ours do. And so she said, although it looked like she had teeth, she in a sense really didn't. And boy, she was just miserable for a few days after that. It was really questioning the wisdom of it all. But the doctor said, just give her a week to 10 days, and she'll bounce back completely. And she did. She eats dry cat food. I have absolutely no idea how. I think she probably inhales it. Okay, so much for polyamides. Let's move on to polyesters and polycarbonates. So same type of treatment. Just like with polyamides, you already know everything you need to know to understand polyesters. We already know that you can make an ester. Well, there's a number of ways of making an ester. You basically treat either an acid chloride or an acid anhydride or even a carboxylic acid, which requires more heat and an acid catalyst. But and any of the above with some alcohol, and you will get the ester, plus a molecule of either HCl or water, depending on what you used to make the ester. But alcoholizing an acid chloride works really well. We already know the mechanism. We went over that in chapter 21. So you know everything you need to know. And we'll just do the exact same trick. So I've just picked a diol and a diacid chloride, whichever ones came into my head at first. And just to give you an idea of what I mean, here's 3 different correct ways to draw that polymer structure. And again, don't worry if you can't copy down every single dot or every single line. This will make it onto YouTube. I'll even hold it there for a few seconds. But these are all perfectly correct ways. You'll see in all of them, I have all of the atoms that make it into the polymer exactly once represented within the parentheses. But they are all absolutely equally correct. I have no preference for any one of those. Any one of those is fine. So as you can tell from this, there's always multiple correct ways to draw any given polymer structure. But this is what I really wanted to focus on, mainly in this chapter, I would say, is drawing the structures of polymers, since they use some other ways in the OWL that I'm not really a fan of. This, at least, I am no polymer chemist, but my understanding is this is the best practice way of drawing polymer structures. And since we love structure so much as organic chemists, I figured it was my duty to emphasize that pretty hard. Good, so much for polyesters and polyamides. Oh, what are some typical uses of polyesters? Let's see. Synthetic fabrics, well, you knew that. Polyesters have been around for probably 50 years, certainly at least 40. And yes, I am old enough to remember polyester leisure suits. Yes, they are as bad as you remember. Actually, I was a very young child then, so I probably had a little polyester leisure suit. I bet you guys would give anything for that picture. I don't believe it still exists, but I must have been cute. I must have been, it probably looked like butter wouldn't melt in my mouth. Okay, so also I have here that sutures are made of a polyester. So there you go. Polycarbonates are a similar type of thing, except we haven't formally introduced the carbonate functional group. Can you believe it? You're going to be learning about like 4 or 5 new functional groups here on the last day. And they just aren't ones that we've needed up until now. But we might as well introduce them. But the way you make a carbonate, there's a few different ways to make a carbonate ester. One of them is to take what's called a chloroformate, which is a special kind of ester that's sort of half ester and half acid chloride. And so you can buy any of a number of chloroformate esters. They're kind of nasty. And you treat them with some alcohol, and just like with an ordinary acid chloride, you'll esterify on the other side. And I said to the other people, I can't think why in practice you would want R1 and R2 to be different, though they certainly could be. I see no reason why you couldn't use or make an asymmetrical carbonate. But carbonates are a special kind of ester. They're esters of carbonic acid, which is, of course, HOC double bond OH. And of course, that molecule is quite unstable. It readily breaks apart into CO2 and water. But the idea behind carbonates is just the same as with making any other kind of ester. Same kind of mechanism. Again, it's a nucleophilic acyl substitution reaction. And you could do the same thing, use a bischloroformate with a diol in order to make a polycarbonate. But another way is to use phosgene, which actually I would recommend against. Phosgene is exceedingly dangerous. It was used as a poison gas in World War I. Actually, I had a kid fact check me on that. He left a note in chat that he had fact checked me on that. It's true, so, but you can fact check me if you like. That one I'm pretty confident on. But there's alternatives to phosgene that are not as dangerous or deadly. There's ones that generate phosgene in situ in the reaction vessel. And those, of course, are preferable if you can get them. But the idea is the same. It's just a diacid chloride. You treat it with a diol, and you'll get a polymer that looks like this. Or, again, there's other correct ways to draw the structure of this polymer. But this type of polymer is what we mean by a polycarbonate. It's just a polymer involving carbonate functional groups. And what are polycarbonates using? Well, I bet you know already. You're probably aware that plastic eyeglass lenses tend to be polycarbonates. But these are all of your sort of crash resistant things, you know, anything that's sort of resistant to impact. Carbonates of lots of different carbonates have good properties in that area. I have here that Lexan is a polycarbonate, for instance. And where are we at? With all this, we might end a little bit early today. I don't suppose anyone will object. But last one is actually going to maybe take the most explanation, so it's just as well that we have time. We have to learn about some more functional groups in order to understand about polyurethanes. First of all, urethane is actually the old name. We used to call this functional group urethanes. Now we call them carbamates. And carbamates are made by treating an isocyanate, which is another new functional group for us, with an alcohol. And this is the one case where actually all of the atoms make it into the product. And that's by virtue of that central sp hybridized carbon that you find in isocyanates. Another thing, and actually I would like you to fact check me on this, this occurred to me just this morning, the very word isocyanate implies that there is such a thing as a cyanate. That's not iso. And I think that's true. The cyanate ion does exist, but I think you'll find that cyanates are inorganic. Please feel free to fact check me on the fly here, as they say, and let me know if I'm wrong about that. But I think you'll find that cyanates are inorganic species, metal salts, metal complexes, things like that. But isocyanates are organic, and so they have this structure. It's NCO, N double bond C double bond O. It's very similar in concept to carbon dioxide, as you can see. Basically, you replace this nitrogen with an oxygen, and you've got carbon dioxide. So it is because of that, because it's such a condensed functional group, that's why all of the atoms make it in. You don't generate any small molecules. Well, same thing with polyurethanes. We'll just take a diisocyanate and a diol. And so I made up that diisocyanate, which actually I bet you can buy. And that diol, you can call that 1122 tetramethyl ethylene glycol. Or if you want that, if you're curious, that's also called pinacol. Pinacol, pinacol, and very easy to get a hold of, very cheap. I think it might even occur naturally. Some of those things do. But in any case, the polyurethane you get would look like this. So yeah, cyanates and ions, see, that's what I thought. So I don't think there's organic cyanates. I think the only organic species are isocyanates. They're saying that to make it clear that the organic group's attached to the nitrogen, not to the oxygen. But I don't think you're going to be able to attach an alkyl group to that oxygen and get something stable. So, but that's the structure of the polyurethane that you get. I should mention, since I forgot to mention this to the last class, and I want to make sure this makes it onto YouTube, I gave you in the class notes the mechanism for getting a carbamate from an isocyanate and an alcohol. I've here drawn it with R groups, but these R groups can be whatever you like. We've seen mechanisms like this before. What this reminds me somewhat of is the DCC mechanism, except it's not nearly as bad as that. It's not nearly as many steps. But we would start by protonating the nitrogen, just because that's going to give us the fewest steps, though this is a resonance stabilized species, and there's other correct ways of drawing it. The alcohol is where used to happening. attacks that central carbon, and now that central carbon goes from sp3 sp to sp2 hybridization. So once we pull off that extra proton, we're done. So it's a very straightforward mechanism. But I did want to point out that I had left that mechanism in your class notes. So yes, so I think that's about it for that. And that might be about it for everything. Gosh, you still have me for 15 minutes. I can't exactly review all of Organic 2 in 15 minutes. I think well, really more like 10 minutes. I think you'll understand that. But if there's anything anyone wants to see an example of, by all means, feel free to ask. I'd be happy to go over something. Tell us exactly what's on the exam is not a reasonable question. I haven't written it yet anyway, but I will. Or if you'd rather just leave, that's fine too, but that's all I have. So unless there are any further questions, it's been a real pleasure, except for the fact that it was online. Thank goodness this is going to go back to normal next semester. But other than that, I hope to see as many of you as are not allergic, or at least not badly allergic, on Friday for Bella Day. Hopefully the weather holds out. So 12:30 in my office, Reed McDonald 308. And like I said, if you are even just a little bit allergic, maybe take an antihistamine just to be sure. Can you give us an example of what the multiple choice might look like? Well, you've had multiple choice questions. No, you've had multiple choice questions from me. Like I would say, you know, here's what's your favorite molecule? Oh no, I don't think I have a favorite molecule. Do I? I don't really have one. Most of them are okay. Yeah, that's another question people ask is, are there going to be, oh yes, if there's mistakes, please send me an email. It's inevitable there are going to be questions that you think are asking about Organic 1 stuff, but you've probably found that on the hour exams also, right? It's impossible to know Organic 2 material without knowing all of the Organic 1 material. So, I mean, I'm not going to go for 50 points on chapter 5, if that's what you mean. But it's inevitable that there will be problems that you think are about Organic 1 material, because it's all one class, just split in the middle. So, but yes, if there's a mistake in your exam, please send it to me. Can you scroll up to carbonates? Well, that was on that page. There you go. Oh. So there's your chloroformate and carbonate functional groups. And like I said, you could use a bischloroformate or I guess you'd have to call it a bischloroformate, or you could just use Phosgene or any one of a few different alternatives to Phosgene. What about your favorite reaction you've done in lab? Oh, that might be a little better. Did you guys do a Diels-Alder reaction in lab? I hope so. I think maybe you did, except that involves cracking dicyclopentadiene, which stinks to high heaven. But that one's really nice. The lab involves mixing, well, I'll need another page. It's a famous lab. It's been done for probably almost 100 years in undergraduate organic labs. And what we would do is we would take, oh, there's my cyclopentadiene, and we'd react it with maleic anhydride, which has this structure. It's just the acid anhydride of maleic acid, which is a super red hot Diels-Alder dienophile, very, very reactive. So I guess now I can't ask about that exact reaction in the final, not that I'm convinced I would have. But now of course, cyclopentadiene is also so reactive, you might recall my mentioning this. You can't buy cyclopentadiene. It's so reactive that given no other choice, it will react with itself. And so cyclopentadiene is afforded as the dimer, which has this type of bicyclic structure. Whoops. And then, of course, your 2 hydrogens going up here. The endo form is the kinetic product, which predominates. But that's the form that you buy cyclopentadiene in. It's dicyclopentadiene. And so if you cook that at a pretty goodly temperature, 100 to 120 degrees, it cracks it, as they call it. It undergoes a reverse Diels-Alder reaction. You get 2 of these. So this reacts like a shot with this. It's one of those experiments that absolutely cannot fail. And I remember telling the students at my previous school, oh, but you don't understand, Dr. Waas, how bad I am at lab. I can get it to fail. No, you can't. It's absolutely fail-safe. But this structure is also bicyclic. And again, I wouldn't say this is my favorite molecule, but it's a cool lab for a number of reasons, which I'll get to. Still need one of those. So that part comes from cyclopentadiene. These 2 are the new bonds that you form. And the maleic anhydride ring adds, you get mainly, again, the endo product. Which adds, I think I'd better, I'm going to try to draw this in perspective, sort of. Ooh, that sort of almost worked. Sort of, kind of. So you get this molecule. And we would then do a number of other transformations on it. This molecule can be recrystallized, but what we would do after this, and we turned it into kind of a puzzle, we would tell them that you would treat this with water. Oh, you see, we didn't tell them the structure. No, that's not true. They had to know the structure of the product. We told them we would have them treat this with water, and this was the really cool part. Of course, like I said, the original, that initial adduct can be recrystallized. It's not often you're recrystallizing things in organic lab, I feel. It's mostly the domain of Gen Chem lab. But it can be recrystallized, and it gives, you know, oops, it's fine. Crystals are kind of nice. But if you treat that with water, of course, you'll get the dicarboxylic acid. Maybe I'll put in my hydrogens first. Oh, that's not going to work. And actually, this dicarboxylic acid is kind of unstable. Unstable to the point that you can't get a melting point, because if you put it into the melting point tube, it just dehydrates and goes back to the anhydride. So it just decomposes. Well, not even really decomposes, it just goes back to the anhydride, which has a nice clean melting point. But the thing I was going to tell you about mainly was these crystals that you get of this diacid will knock your socks off. They are the coolest crystals ever. They're long, beautiful white needles. You can get things that are like that long. And as long as you're patient and don't mess with it, you know, you can get things that look like little white sea urchins. It's really, really cool. And since I had the 1250, the part that we didn't tell them was that when you treat this with sulfuric acid, that would have made a good final exam question. I guess it's ruined now. What happens is you get an alkene addition reaction of all things, one of these 2 carboxylic acid groups. And so That's kind of funky looking. And we gave them all the spectra, and their job was to figure out the formula, or rather the structure. So you get this lactone. A lactone is a cyclic ester. So that's what you get. Draw me the mechanism. Well, but yeah, that was kind of, some of them did figure it out. I think what we generally found was like 2 or 3 people figured it out and everyone else copied off them. So, you know, little brats. Anyway, so yeah, I guess that's about all I have. So like I said, I'll be doing my office hours later today and also tomorrow. And as long as the weather holds up, let's hope for that. Then we'll do Bella Day on Friday. But like I said, if you don't specifically hear from me otherwise, let's also hope and pray that Howdy gets back up and running, because I'm really hosed if it doesn't. I need to do my grading. Other than that, it's been a pleasure. We'll see you all later. Hey, next semester, since we're allowed to meet in person again, if something brings you by Reed McDonald, don't be a stranger. You know where to find me.